Hello everyone, this is Mr. Taylor with Young Engineers of Today. What we're going to continue looking at is ancient engineering with a focus on catapults. This is our part 2 of this topic. Just to recap, compression and tension, the ability of a bow depends on its ability to store that energy. Remember, compression is a pushing force, tension is a pulling force. When you talked about the traditional bucket catapult that uses built-up tension in the ropes, and these catapults are using wood and rope because it does very well with tension. More energy stored translates to higher velocity of an arrow release, which means more damage. Then we started looking at how elastic energy is used within bows and arrows in this evolution. Here is looking at force for draw curve, looking at pull back string further, and you can see how this evolution keeps occurring. Also looking at pre-tensioned bowstrings versus normal bowstrings. Increasing stiffness of the wood. You can see how that's affecting the pulling force and draw length. Now, there are important limitations to be aware of. Bows must be strong enough to carry the maximum pulling force without breaking. What does this mean in terms of improving design? Bow makers had to make new discoveries. You could look at this as materials engineering. Bowmakers discovered they could strengthen the bow and even more if they combined wood, animal horn, animal sinew. The third one is tendons from animals. Horns hold up much better to compression. So it was added to the inside of the wooden bow, while sinew holds up better to tension, so it was added to the outside. Okay? So improving this design of the bow. Now, compound ruler bow. This is in your in the book, Many Weapons of Mass Destruction. 3. It's purple. You can go ahead and build this. Remember, safety first, eye goggles, any sharp tools or instruments, hot glue guns, etc., drills. Make sure you're using the support of an adult. All right, and you're making this with a skewer, a pen cap, a pencils. I should say. There's one here and one here. Tape, plastic ruler. Let's cut in half. String or skewer. And the thing is, be the engineer. Hack it. If you want to use a rubber band instead of the string, or you want to change out different materials, go for it. Okay. Now, compound bows. Now, limitations are physiological, meaning humans were limited by their own bodies. And I want you to think about what some of these are. All right. Now, some of these would be the length of the archer's arm. Your arm can only be pulled back so far, and if you have a longer arm, you have a better opportunity. Now, strength of arm, chest, and shoulder muscles. If you have more built-up muscle in those areas, it's going to make it easier versus those who don't. Strength and dexterity of fingers. Okay, some of these limitations. Now, because of these limitations, the best possible bow required 45 pounds to pull with a 20-inch draw range. Now, as you can see, the traditional versus the compound bow. Okay, we're getting a lot more draw length versus pulling force. Okay. Now, back to this think tank that we talked about last class that took place in ancient times. So, was the group going to advance bow? How was this group going to advance bow and arrow technology? Well, the first solution was this belly bow, the Gastraphetes. All right. As you can see here, you have your bow section with this area, and we'll look at this in a moment, and where you would launch your large arrow from. As you can see, the archer is pushing down on it and loading it. And this is increasing the draw length by using this latch system here. The further it gets pushed back, the further that latch is. All right, now here's your trigger. Now, advancements in progress. Weapon makers continue improving this belly bow. And what did they do to make it better? Let's see. They made it bigger, of course. This development led to technological advancements that made the first true catapult possible. Okay. Now, we always think the catapult, the first one, being the traditional bucket launcher, but it actually wasn't. You had this stiffer bows made cocking the weapon more difficult, so a wandless was added to the back of the weapon to draw the arrow back. Okay. Zopyrus bow machine. Now, while this allowed for large arrows, now the entire weapon needed to grow in size, making it unwieldy as a handheld weapon. A base was added. So we actually evolved this weapon for larger destruction, more powerful, increase the accuracy. It wasn't limited by human physiological aspects, but the flip side of it, it turned into this mass weapon now. Now, as you can see here, the bow on the first model of the catapult were maxing out the size that artisans could make them. Basically, this is limited to what they physically could do, the tools they had, the trees that were available, etc. Now, which leads us to the gift card Ballista that's in the Mini Weapons of Mass Destruction in Volume 3. Typical safety requirements: always wear eye protection, never substitute metal, tableware, or plastic, never launch at people, animals, or things of value, only use these at home, ask for help using potential harmful tools like a knife, hot glue gun, wire cutter, electric drill. Alright, here are some of the supplies, and if you don't have all these supplies, switch them out, make it work for you. A 1 expired or 0 balance gift card. You can use playing cards if you don't have gift cards, or you could use like cardstock and reinforce it. A binder clip, a plastic milk jug cap, a push pin, a wide rubber band, tools that you're going to be using: safety glasses, marker, scissors, single hole punch, hot glue gun, hobby knife. And you're probably going to need a measuring tape as well, or a ruler in here for measurements. And ammo, you're going to use 1 plastic cotton swab, just a good old-fashioned Q-tip. All right, here's step 1. Locate an older 0 balance plastic gift card that you're okay with destroying. With scissors, cut 2 half-inch horizontal strips from the card using a single hole punch to make 3 holes in one of the strips. 1 in the center and 2 1/8 inch from the opposite end. Center the other strip on a large card section as a guide. Once in place, cut 2 90-degree 1/4 inch slits opposite from one another, approximately 1 inch from the end. The dotted lines represent the fold lines for the next step. Okay, and then there's your image here to help you with this process. Step 2A. The front of the card will be folded 90 degrees up. The 2 slits are the fold lines for the bend. Step 2. The second set of folds will be the back section. They should be folded down to a crisp 90-degree angle parallel to one another. Using the 1/4 inch slits, make these 3 folds. Large section, as you can see in the image. Step 2B, with a hole punch, make 1 hole centered in approximately 5/16 of an inch, almost 1/4 of an inch from the bottom of the front folded up face. Then carefully hot glue the 3-hole strip to the upright lying center hole. Next, carefully hot glue the small binder clip to the back of the assembly as shown. Now, if you don't have hot glue, you might have super glue. You might have really good tape, and you might have to just change the way you design this, okay? All right, you're the engineer. Hack it. Now, step 3A. The last 1/4 inch card strip will be bent 4 times into a functional support of the Ballista. Now, this is a little bit more trickier aspect. The first 2 45-degree bends should be made approximately 1/4 inch from the opposite ends of the gift card strip. The second group of bends will be 1/4 inch from the center of the card at 45 degrees opposite from the one. You might need a little bit of help doing this just to get the bends right. Now, step 3B, once completed, the center of the card should be a 1/2 inch wide area from the push pin connection as shown to the right. Connect the frame support to the base by placing a push pin through the center of the frame supporting the milk jug cap. Once connected, carefully hot glue the Ballista frame into the folded support. And this is your assembly process here. Now, this is the actual weapon assembled. Only thing left to do is to put the rubber band. You're going to cut that here. For the Ballista, you'll be using a rubber band booster, and this is non-traditional. Cut open a wide rubber band and then tie both ends of the rubber band to the opposite ends of the bow using the outer holes as the rubber band tie downs. The mounted rubber band should have minimal slack because you want that tension in the rubber band. Now, to make your ammo, cut off the end of the cotton swab with scissors, then with scissors or a hobby knife, make one small slit cut and end the cotton swabs handle the nock detail. See that nock, if you ever see arrows, they have a knot on them that you can wrap around your bow cord. It helps with control and firing. All right, step 6, it's all done, just fire. Remember, wear eye gear and do not aim at anything living. In the whole process of building this, if you need adults, have adults support you. Don't use tools without looking at them, and having adult supervision and safety is always extremely important. Okay? All right. Now, catapult development, composite bow temporarily meets its limits. Developers must now turn to fundamental different ways of storing elastic energy. This path led to the Torsion Catapult. We'll look a little bit at this and then finish this up in an upcoming video. Torsion Catapult development occurs over a series of discoveries and advancements starting in the mid-4th century. By the end of that century, we have the arrow-shooting weapon called the euthetone and the stone-throwing weapon called the palanton. Here are they, on the left and right, correspondingly. Now, torsion springs. Much of the hardware looks the same, stock, ratchet, trigger, wandless that we learned about earlier in the previous video. What's new are vertically aligned torsion springs. Torsion is this twisting of a beam or structural element, as you can see in the image. Torsion springs become the primary storage for elastic energy in this device. What used to be the primary storage? If you remember back, it used to be rope and wood. Torsion springs in a palanton consist of bundles of rope with a wooden arm thrust through the center. Now, what materials do you think was used for this rope? Think back to when we talked about materials that could withstand compression tension. Once again, as I said, rope and wood. Here are the images of this. Now, this is the spring broken down into its pieces. Okay. See how this is working here? That's where you pull back on it. And we will continue with this in an upcoming part 3 video. Thank you and have a great day. I'm Mr. Taylor with Young Engineers of Today.